So, for those of you who still haven't noticed, I've put that calendar in course information, okay? So if you're not going to be here, if you miss days, hopefully I'll try and update this as much as possible. So today we're moving on to example 50. Alright, so we ended last lesson talking about if we have a of f of x, then that is a vertical dilation. We're pulling it in my y direction, kind of like stretching out a slinky. So we pull it in our y direction. Now, the transformation, just because it's on the previous page, let's make all these skinny. There we go. There you go. These are all really skinny. I don't know why. I didn't change them. Yeah, sorry. This is really entertaining stuff. So for the transformation for this, we are talking about f of x take c. Okay? Again, for every transformation, this will have the same, for every function, this will have the same effect on the function, but we just need to start recognizing what we're doing. And I'm just going to start by, again, filling out what these functions should be. So if f of x is equal to x squared, putting in negative 4, we get 16, 9, 4, 1, 0, 1, 4, 9, 16. And a round of applause, because I didn't stuff it up this time. So now this is the important part. Last time we put the value of f of x down below and then we changed it. But we're not changing f of x right now. We're actually changing the x value. So now we've got the f of x plus 2. So that will be reading f. Well, what's x plus 2 when x is negative 4? Negative 2. So it's now f of negative 2, which is 4. This is going to be f of negative 1, which is 1. This is going to be f of 0, which is 0. And so you go along, keep going like that, and then you're going to get that this is f of 1, which is 1. And then I'm just going to fill out the rest of them because we can get an idea of where this is all going. Below, we have the value of x take 1. Again, we would changing the x value of my graph. We're changing this negative 4 here. We put that down there into our x value, negative 4 in here. So now we're finding out the function at negative 5. Because negative 4 take 1 gets negative 5. So that answer is 25. This is going to be f of negative 4, which is 16. And then we can understand how the rest is going to go. 9, 4, 1, 0, 1, 4, 9. So now we want to try and plot these. So I'm just going to start with my first transformation that I'll label in red. So when x is negative 2, when x is negative 4, the function is at 4. So we go negative 4, 1, 2, 3, 4. Be really careful here that you're not plotting at negative 2. Because we're not actually finding it out when x is negative 2. It's when x is negative 4 here, but we've added 2 onto it. So that's what you need to be careful of, because then you'll just be plotting the exact same graph that's already there. When x is negative 3, we go to 1. So negative 3, 1, 2, 0, 1, 4. And then this should go up to 9. And then we can sketch from here. And it'll look something like that. Alright. Next one, shall label in blue. When x is negative 4, it's 25. So negative 4, 25, you can't get that. We'll start at negative 2 because that's going to be 9. So negative 2, 9. Negative 1, 4. 0, 1. There. And it's 4 when 9. Oh, I shouldn't have done it in blue. I'm going to be really annoying, and I'm going to go orange. Just because I don't want the two blue graphs there. So we should probably all know what this transformation already does because we've seen this transformation so many times, okay? But when we take a value away from x inside my bracket, so when it's f of x take away c, it just translates it that many units. So for my first one, for x plus 2, what's the transformation that happens? We move, where, Ollie? 2 to the left. For x take 1, where do we move, Damien? Move 1 to the right. So for the transformation x takes c, we move c units to the right. And again, we can do this for any function we want. It doesn't matter what type of function this is. So we looked at quadratics before. We could do it with cubics. We could do it with quartics. Or we're going to have a look here. Again, I'm not familiar with that function. So vertical line test. Anywhere I go across, you see that I'm only ever going to intersect once. Only ever intersecting my graph once, no matter what value of x I am. So therefore, that is a function. So now it says that we need to find the graph, the transformation, when it's f of x take 3. If it's f of x take 3, what transformation has happened? Where are we moving? Pat. Where are we going to be moving with this transformation?
To the right.
3 units to the right. We move c units to the right. If we take away c, take away 3, we move 3 units to the right. So it's really quite simple because it just goes 1, 2, 3. That's a dash. 1, 2, 3, b dash. 1, 2, 3, c dash. 1, 2, 3, d dash. All I'm doing is just moving each individual point 3 units to the right, which you could do up here as well. You just go there. Well, just go that way. Just go that way. Here instead, we're now moving them all. And then don't forget to connect them. There we go. And then connect. And so it's the exact same graph, but it's just a little bit to the right. Last one out of our transformations that we're going to talk about is when there's a constant inside that bracket. So let's just complete the normal table. Again, 4, 1, 0, 1, 4, 9. Quite easy. Now, also let's just cross this out here. This is supposed to be f of 0.5x. Just a bit of a typo there. And this is supposed to be f of 2x. So, same thing as before. We're not changing our function of x. We're changing our value of a function when x is negative 2. So when x is negative 2, I'm going to put it into this f of 2x. So what am I actually finding? The f of 2 times negative 2. The f of negative 4. The value of the function when x is negative 4, which is going to get me 16. Here, the value of the function when x is negative 1 is negative 2, because I'm timesing negative 1 by 2, times 2 by negative 1, gets me to the value of function 2, so 4. That's still going to be 0. That's going to be 4, 16, 36. Now, what if I'm doing a half? So I'm now going to figure out the value of the function at a half. So if I put negative 2 into 0.5x, what is going to be left over? Justin? Sorry, Samuel? Negative 1. Because I'm dividing negative 2 by 2. Here would be negative a half. This would still be 0. This would be a half. And so on. You're just dividing them all by 2 as you go across. And so I can negative 1 squared, that's quite easy. That just gets me to 1. I don't know why these are like changing on me. What's negative a half squared, Colton?
Like 1 squared, like 1, or like...
So it's like 1, or it's like 1 squared, or it's like What's a half times a half? 0.25, or 1 over 4. So this is going to be 1 over 4. 0 squared is 0. Half squared is 1 over 4. Then that's going to be 1. What's 3 divided by 2? 1.5, or 3 over 2. What's 3 over 2 squared? Ollie? 9 over 4. Alright. I always just get decimals out of your head. Especially in this course, algebra-wise, your algebra will improve better if you can do it with fractions. Because 1.5 squared is 2.25, or 3 over 2 squared is 9 over 4. What one's easier? 9 over 4 and 3 over 2 squared. So just try and ease yourself from figuring some of these things out. So now we're going to plot these on our graph. When x is negative 2, f of x is 16. So negative 2 goes up to 16. Next one is that when it's negative 1, we go up to 4. 4, 16. And it looks like that. Now I'm going to label my other one. It's still going to have that point 0, 0. 1 gets me to now a quarter. So that's not really going to help me. I'm just going to go to 2. 2 should mean 1. 2 here should be 1. And 3 gets me to about 9 over 4, which is just above 2. So I'll be like there, about there. And then we can sketch from there. It'll look something like that. Now, what do we think has happened here? We think we shrunk it, so we think we're shrinking it down. Well, wouldn't that be a dilation in y? if we shrink our function down, doesn't that look like our dilation in our factor of y? When we think about it, we're actually stretching it out along the x-axis, which is why we're changing our x value. The transformation changes the x value, so that's what we're doing. It's important to remember that a of f of x does not equal f of bx. These two transformations are not the same. One changes the value of y, one changes the value of x. Our a dilates parallel to y. This dilates parallel to x. If it's inside of our brackets, it only affects x. If it's in front of that f of x, it is changing our y value. If it's adding at the end, it's changing where we are on our y-axis. So again, let's find out what these are. So we want to... This is where it may be a little bit different. So I'm just going to start with the point A. So we know that the point A... Can someone give me the coordinates of point A? How about we look here? The coordinates are -7, -4. Okay, just look at our table down here. And we know that f of x, so f of -7, is equal to 4. That's how all of this works. We are not changing the y value. So we're not actually changing our y value because we know we're affecting x if we're inside of our brackets. So we need to find the number where f of 2x is equal to -4. And sorry, that should be negative up here as well. So that should be negative. Our transformation inside of our brackets only changes our x value you put into the function. It doesn't change y at all. So we need to now find the value of a number x where f of 2x is equal to -4. How are we going to figure that out? Any ideas, Riley? We don't want to divide -4 by 2. You want to divide -7 by 2. We know that 2x has to equal what? It has to equal -7 because we know that the function only spits out one y value for every x value. We know that it has to be -7. So 2x has to equal -7 because otherwise the function doesn't stand. So x is going to be -7 over 2. And that's going to be my new coordinate down here. So I know I just have to divide that x value by 2 to get it down here. My y values are still always going to stay the same. That's -4. That's -4. That's 2. That's 2. That's -2. That's -2. That's 4 and 4. The only things we're going to be changing here is the values of x. So what should my x coordinate for this point B dash be, Nishk?
-4 divided by 2.
Yeah, -4 divided by 2, so -2. 0 remains at 0, and then 6 divided by 2, so 6 divided by 2 gets me to 3. So now I figured out those ones, I'm going to go into yellow and figure out the next ones. Well, now we're not f of 2x, we're f of -x. So what do you think we'll be doing to all of our x values? Gleason, what are we going to be doing to all of our x values if it's now -x? Yeah, we're just flipping the signs of all of our x values. So that now becomes +7, that now becomes +4, that's still 0, and this is just -6. So now we're going to want to plot all of these values now. So -7/2, that's in between 3 and 4, so it's going to be there. And then we know that that's at -4, so we're going to start our point there, A dash. -2, 2, and that's B dash. 0, -2 will still remain 0, -2. And then 3, 4 is here, and that's D dash. And then I'm just going to connect all of them. And now we can clearly see that we're not stretching anything out in the y-axis, we're actually squishing it in our x-axis. All of our points are much closer together to that y-axis, which means we're squishing parallel to x. We're getting closer together. Now, if you have a point that's going to be on the y-axis here, so if you have a point that's going to be here, that's always going to stay the same if you're dilating parallel to x, because you can't stretch out anything that's at the start, okay? It's like if you hooked a resistance band to a wall, and then you're pulling it as hard as you can get, that's always going to stay hooked to the wall. You can walk closer to it, it's always going to stay hooked to the wall. Now let's go the other way around. 7, -4. 7, -4. This is now A dash. 4, 2. 4, 2. B dash, that's the new C dash, and then -6, 4. 1, 2, 3, 4. D dash. What's happened to that graph here? It's been what? There's a special word for it, guys. It's been reflected. It's been reflected on the y-axis. It's exactly the same shape, but we're just the other way. Okay. So now we have these graphs all plotted, and we have a bit of an idea now what these transformations do to the graph. So now let's describe all of our transformations. So for my first one, when it's f of 2 of x, remember the language that we need to use. Okay, so it has been dilated by a factor of... What is the factor in which it's been dilated by? 2? Well, if I scroll back up, are we getting wider or are we getting more squished in? We're getting more squished in. Does that mean we're getting bigger or does that mean we're getting smaller? It means we're getting smaller. Because it's inside of that bracket, it changes how I would go about it. We're actually dilating by a factor of 0.5 parallel to the x-axis. And then for the next one, again, use that same language we need to use. dilated by a factor of -1 will still just be -1. Parallel to the x-axis. Or what's another transformation we could call it? Or reflected in the y-axis, yeah. Reflected on the y-axis. Important thing to remember, I'll just put it over here. Negative f of x and f of negative x. One reflects in y, one reflects in x. Which one do we think reflects in y? Bottom one, guys, we just did it. If it's a negative x, we reflect on our y-axis. If it's a negative f of x, we reflect on our x-axis. So negative f of x reflect on the x-axis. F of negative x is reflect on the y-axis. Okay. So, from this investigation, we can see that f of b of x, when we have a constant in front of my x, it's a horizontal dilation. It's a dilation parallel to the x-axis of the factor 1 over b. So now we have all of this. Essentially, we've gone through the whole booklet just for me to tell you this. Okay? We can put these transformations together as a general equation for any function. Because I've written it as f of x, that can be any function. It could be a linear function. It could be a quadratic function. It could be a cubic, or so on. But all the transformations together will look like that. A is a vertical dilation. So imagine stretching a slinky and we're stretching it up and down of scale factor of how much we're multiplying it by. D is a vertical translation of d units. We're going up or down. So if we have a constant at the end of that formula, we're just going up or down the y-axis. A and D only affect the y value. Because we're dilating by a factor in the y-axis, it affects the y value. Because we're translating, it affects the y value. Those two only affect the y-coordinate. The other ones only affect the x-coordinate, which is why our transformations are parallel to our x-axis. Okay? Now, there's one more example in this booklet, 54, and it's asking us to see how transformations will act under different points on a graph. We're not going to do that today. We're going to do that tomorrow after we've done a bit more examples of transformation of graphs. Good news is, that's functions. We're done with all of this. Okay? Transformations, circles, parabolas and y, all of this stuff, we've now done it. Okay? Now we just need to focus on getting as many questions done as possible. So, Sadler 7b, Sadler 7c. It's our task for the next couple of days to get all of that Chapter 7's questions done, because we should have learned everything we need for it. There's also a bunch of worksheets